I'm a software engineer and I want to spend the next 20 minutes to talk about memory management. So my talk consists of 4 parts. I will start with the general theory that does not only apply to JavaScript but also to other languages like Java, Python or even C, at least a little bit. In the next part we will see how we can use the Google Dev tools to see how the memory management works in action. And then we will learn about some patterns that can cause problems with memory management. And here I will speak especially about the memory leaks. And in the end, I will explain a little bit how the garbage collector works. Good. So as you can see, I have here a JavaScript object that stores 2 properties. And if I want to access this property sometime later, I need to store it somewhere. And that somewhere is usually the main memory. But this is just a very simplified image. A more realistic version might look like this. As we know in JavaScript, we don't have any commands to store the data into the memory, but this does not mean that it is not required. And the thing that is responsible for the storing is the engine, because as we know, our JavaScript code is run by an engine. But the engine, it does not have direct access to the hardware itself, only the operating system does this. And what the operating system now provides to a process or also to the engine, it provides something that we call virtual memory. And the applications can put their data inside or into the virtual memory, and the operating system will map the data from the virtual memory to the actual hardware. Now, in order to structure the data that is inside of this virtual memory, we have to use data structures. And there are 2 major data structures. The first one is the stack, and the stack is also called the static memory allocation. And the stack comes with a constraint because when we want to use stack as data structure, we have to know in advance how much memory a function will require, and this also includes all the variables that it will create. And what the stack does is that it will allocate memory space when the function starts to run, and when the function exits, it will remove all that memory. Now, this is a kind of a problem for JavaScript, because in JavaScript we don't know in advance how much memory our function will require. And of course, we also don't want that everything is removed once a function exits, because we can have some objects that we want to have returned and that we want to continue to work even when the function has already exited. And that's why in JavaScript, mainly more or less everything, not really, but the major things are stored in the second data structure that is also known as heap. Now the problem with the heap is that the heap does not automatically remove the memory. This is something that we have to do. And since again we don't have any commands in JavaScript to remove memory, it falls again into the responsibility of the engine. And the part of the engine that is responsible for the removing of the memory is called the garbage collector. So the garbage collector is able to detect objects that are not being used anymore and also removes it automatically for us. So from now on, when I speak of memory, I will mainly mean the heap. Good. So the question is, of course, now how large is such a heap, when it is too much, when it is too few, when it is optimal. The answer is, of course, it depends. And I have here a list of most of very popular websites. And as we can see, the Google search requires only 7 megabytes. And on the other hand, we find Google Maps with 3D enabled feature, which occupies or allocates about 150 megabytes. So your applications should find its place somewhere in between. Now the next question is, of course, how can I measure how much memory my application actually requires? And this can be done very easy. So I have here an empty HTML page that doesn't do anything. and I have here Chromium. So what I have to do is that I just have to open the DevTools, and then I have here this tab called Memory. And if I scroll down, I can see here two very important numbers. The number to the right is the amount that the engine has allocated for the complete heap. And the number to the right, namely the 1.3 megabyte, is the memory that is actually already used. So we have here an empty web page that is already using about between 1 and 2 megabytes. And this is because JavaScript comes with some static objects, with some static methods, and so on. And you can see this as the minimal memory footprint of JavaScript in Chrome. Question, of course, is now, okay, now this is an empty web page. Can I somehow measure, for example, if I have here an object? So I'm adding a script tag. Like this. And then I have here an object that is called person1, and this person1 contains multiple properties with different data types. So we have here 2 times a string, we have one date, we have one boolean, but we also have a function. And I want to see now, or I want to know how much memory this object requires. What I have to do, I have to go back to Chromium, reload the page, and then I have here to the left, I have the button Take Heap Snapshot. And if I click on this button, then what's happening is that it goes through all the objects that are inside of the heap, groups the objects, and gives me a list. And since the person1 object is directly attached to the window, I can open this one, expand it, and then I have here all my objects that can be reached by the window. And if I scroll down, I see here already the person1 object. Now, this screen comes with 3 different columns. First one is distance, and distance means that is the distance from, so how many steps are required to get from the window object to this person1 object. So window object counts for 1, and then we have here person2, and that's why we have 2. And all the properties inside of the person1 count for an additional step, and that's why we have here 3. The other column is the shallow size, and the shallow size is just the memory that the object, the shell itself requires. But of course, what we are interested in is the retained size. And the retained size is the object, including all its properties. And we can see here that the memory size for the person1 is about 1,600 byte. So, like this. Good. So we have seen now how we can get the information how large an object is, but of course we are also interested how the memory consumption of our application changes over time. So what I want to do is that I want to create a button. If I click on the button, I want to execute a function, and then I want to watch how many memory this function does require. So this is my button, then some CSS so that it looks nice. And then I have prepared a function that runs another function 5 times when the user clicks on it. Just removing this. And what I do is that I now create an array that I call large array, which is empty. And then I say I want to run following function 5 times, where I'm adding a new array to this large array, or pushing it, and that we see some memory consumption. I'm creating a memory that contains 100,000 elements. Okay. So if I go back, I can reload my website, then I have here my button, and then I have to switch the tab and I go to performance. And in performance, I have again a recording button, and if I click on this, the memory consumption is being watched. So click, and I say click me, and it runs 5 times. I can say stop, And then I see here very nicely how the memory consumption increased over time, namely the 5 times. So we started from about 2 megabyte and then we went up to 6 megabyte. The only question is, this memory stays at 6 megabyte. Why? Because the large memory is in the window object, so it is more or less globally. Everybody can access it, and that's the reason why the garbage collector does nothing. So if we want to see the garbage collector in action, I just have to remove the large array, and I'm creating these arrays just out in the blue. So I'm just creating them, but they can't be used. Reloading the website, removing this. Then I say here, and then I say record. Click me. Again, it runs now 5 times. I have to wait a little bit. Then I stop it. And then we can see here again the increase of the memory consumption, and then it went down. And this is the time where the garbage collector kicked in. The garbage collector saw that we had allocated quite a lot of arrays that aren't used anymore, that can't be used anymore, and that's why they got removed. Good. So to the memory issues. So we have seen now how we can watch how the memory works, also the analysis tools. And the major problem that comes with memory management are the so-called memory leaks. Memory leaks means that we have some objects lying around that aren't not used anymore, but the garbage collector can't remove it for some reasons. So one of the reasons is that an object is defined in the global scope, as we have just seen with the large array. This means that the garbage collector will simply not remove it. Please be aware that there are some pitfalls where you can accidentally assign an object to the global scope. If you forget to use var let const, something like this, or if you are doing some strange things with the context, it can also happen that the context changes to window. So please be aware of this. Then we have also another problem which comes with detached DOM nodes, and this means so we have to know that the rendering engine itself also has a separate garbage collector, and the garbage collector for the rendering engine works like this, that it removes all the nodes that are not part of the DOM anymore. But what can happen now is that in JavaScript we have a reference to one of these DOM nodes, and then the garbage collector of the rendering engine knows that there is a reference from JavaScript and can't remove it. And this is a very hard to find bug or issue, and that's why in the heap dump there is a special functionality to find these detached nodes. So if we create or make a heap dump, as we have seen before, we only have to type into this input field here detached, and then Chrome lists us all the DOM nodes that are detached from the DOM, and then we can check if we can really remove them or if they are there for a reason. So these are more or less very easy to debug memory leaks. It gets harder when we come to the closures. And this comes again with a code example. So what I want to do, or let's consider we have an application where we are requesting data of the current user from an endpoint. And then we have again our button, and if we click on the button should just print out the name of the user. So I'm simulating here where I'm loading the endpoint. As we can see, it returns a promise that contains an array. Only the first element of the array is the actual name of the user, and the rest is something else. We don't care. And then we have a get current user function, and this function should return me a print name function that we will use as event listener. And what I'm doing here is that I say, okay, name, I have here this nested function getName. I'm just calling it. This getName will just return me here the first element of the list, which will be the name. And then I return a function printName. And what this function does is that it just says console log hello name. And of course, I also have to add it to the event listener, or I have to create an event listener. Looks like this. So I'm creating my getUser function by calling it. And when I have my function, I'm adding the event listener. And yeah, let's see how this works. So I'm reloading it. I'm saying record. Then I say click me. I can already say stop. And as we can see here, it prints out the name, so the function already worked. And if we go back to the performance, then we see that nothing really changed. There was no increase in the memory consumption. But there is something very, very strange, because the heap size is already at 12 megabyte. And yeah, I mean, obviously it must have to do something with this big data object, but the question is, of course, why did this happen? So what we can do is that we can go to the debugger. I set here a breakpoint, and then I'm clicking again on this button. So everything looks nice so far. But now the thing is that inside of this closure, we have this data object. And this is what that causes the garbage collector not to remove that data object. And the question is why. So as we can see, we have here this getCurrentUser function, and this getCurrentUser function contains two further nested functions, namely the getName and the printName. When the function exits, we would suppose that the getName function can be removed because it is not required anymore. And since only the getName accesses the data, we would also guess that the data object will be removed as well. But this is not how it works, because what we have is that we have here the scope, and the rule is that all nested functions, they share the same scope. And as we can see, since the getName needs access to data, the data gets into the scope, and then the printName accesses the name, which also gets into the scope, but the printName function has now also this data object inside of the scope, and this causes all the troubles. So the question is now, how can we get rid of this? And the answer is very, very simple. We only have to define a way where no nested function contains the data object, so that it looks something like this. If I go back to my code, I'm removing this return, and then I'm simply doing the thing that this nested function would have done. I'm just saying get the first element. Yeah, just running it, reloading it. Then I say again, click me. And then we can see that in this closure, the data is not there anymore. And again, the problem is not that we have such a big data. The problem was that the data was used inside of another nested function, and this caused that the data find its way into the scope that is shared by all nested functions. Okay. So this is just And again, this is a rule an exception to the rule, because if we are using an eval in a nested function, then this will cause the engine to put everything inside into the scope, because then maybe this eval will try to access the data for some reason, and still remember, just don't use it. And the takeaway is here that closures, they are a very, very elegant way to solve certain problems, but they are also very dangerous when it comes to memory management, and it somehow looks like a pact with the devil, so you really have to know what you are doing when you have many closures inside of your application. So I think we are already over time. Okay, because I have one last chapter, and this is the garbage collector. So we have here again another example where we have some shopping case, and as we can see, we are defining here a basket that contains basket items. We create a total object that wants to calculate the total number of the total amount of money that we have to pay for the basket, and then I'm iterating over each basket item, and in each iteration, as you can see here, I am fetching the product from some endpoint. And then I use the price of this product multiplied with the amount to come to the total amount. So it works like this. We start with assigning with creating the basket. As you can see to the right side, we have here the heap, which started out to be empty. Now we have the basket inside of it. Then we create the total, and then the loop starts. So we create a new product object. Then the next iteration, we create the second product object. Then we have the third iteration. And what can happen now, since these await commands took quite a long time, that the garbage collector kicks in. And what's happening now is that the garbage collector says, okay, execution stops immediately. Nobody is allowed to do anything. And the garbage collector follows now something that is known for mark and sweep, as mark and sweep. And the garbage collector, of course, knows which objects are in the heap. And the garbage collector now tries from predefined routes if these objects are reachable. And one route is the window object. The basket, actually no object of this list can be reached by the window object, but what also counts is the current stack. And from the current stack, we can access the basket, we can also access the total, but not the two products that have been created in the iterations before. And now the first ones are marked that they should stay there. Now the obvious thing which we might think is that we just have to remove here the product, the first and the second product object. But this is not how it works. In reality, we have a second heap space, memory in the heap. And what the garbage collection now does is that it takes the objects that will survive this garbage collection, namely the basket and the total. It moves them into the second memory space. The second memory space, which is also called to space, becomes now the active heap space. And what happens to the first? We just remove everything. So you can think of this like if you have a house, you want to clean your house, you just take all your belongings, put it to a second house and burn down the first house. This is a little bit crazy, but it is done with the garbage collector, and the reason why it works like this is an effect we call infant mortality. And this means that we know that the most objects that we are using, they don't live for a very long time. So it is very, very inefficient if we just go through the heap and pick each of these objects. And therefore, we just take the few objects that we know will survive, put it to another memory space, and just remove the rest. So this is how it is usually done. So I'm just skipping it. And then there is one more thing with the garbage collector. Let's suppose there are now more purchases in the basket. So it can happen that inside of this for loop, we have multiple garbage collections. So it just behaves as we just have seen. So the survivors are moved into the other heap space. But what happens now is that the garbage collector knows which one of these objects have already survived one garbage collection. And they are put into a so-called second generation, which is called intermediate. And the ones that have just been created are put into the nursery generation. And if the objects from the intermediate generation survive the next garbage collection, then they will not put again into the other heap space, but there is another one, a far larger one, and they will be moved there. And the larger one is called the old generation, and the first two ones are called the new generation. And why are we doing this? Because the old generation contains these objects where we think they will survive for a very long time. They have their own garbage collection cycle, and we just try that inside of these two smaller memory spaces, we have only the ones that will not survive that often, so that the garbage collection cycle itself is very efficient and can be executed very, very fast. Okay. This was just really just scratch the surface how it's working. In reality, it's a little bit more complicated. There is far more, but the principle, it stays the same. And what the browsers are not trying, the browser vendors, what they are trying is that they want to reduce the time that the garbage collector takes to more or less, this is an effect called stop the world, where nothing can happen. And what they are trying, that they try to put some of the work that has to be done before the garbage collection actually really starts, so that it just takes a very, very short amount of time, which means we have some garbage collection tasks that run concurrently or in parallel and so on. And especially in the browser, the garbage collection also works together with the rendering engine, and the rendering engine can tell the garbage collector that we are now between a rendering frame, for example, and that the garbage collection can now do something which goes unnoticed by the actual end user, because there is no flickering or something. Good. So this was everything from my side. Well, thank you very much. And if you have questions or if you think that something is wrong, just please tell me.